Hello, everybody. Thank you very much for inviting me to this conference. So today I will be presenting my work on a simplified protection scheme for renewable energy and integrated AC microgrids. So my name is Ahmed Usman. I'm currently working as an assistant professor in the electrical and computer engineering program at the Dhanani School of Science and Engineering at Habib University. This work has been done as a senior year design project by my students, Syed Zain Abbas and Muhammad Talha Shahab. So let's start with the presentation. So first, the question is why we are using or why we are moving towards the renewable energy system. So overall, we can see that the primary reasons are the climate change. That's the big issue we have these days, and with the increasing cost of fossil fuels and their impact on the climate are affecting our day-to-day life. So what we have seen over the years, and that is also showing in this graph, that in 2015, the percentage of renewables we have, such as solar, biomass, hydro, wind, has increased, and it is also projected to increase as by 2035. And when we are increasing these renewable energy resources in our grids, one of way to realize this is to have a concept, or is to use the concept of microgrids. It is becoming difficult for the governments and for the agencies or for different countries to run a complete grid or centralized grid. And what they are doing is they are decentralizing the grid. We have seen this effect in the United States and in United Kingdom, where they have brought in multiple entities to share their network and to supply electricity to different consumers. So, and that also reduces the burden on the government in many aspects. So, microgrids, we can see, or we can also say that that it's a way ahead for Pakistan. What we have with us is that data from US from 2014 to 2018, sorry, is that they have seen 15.4% that the critical operations that require uninterrupted power supply has improved. 51% improvement have experienced in the increase in betterment in the electricity outage. So these sort of benefits, when they are given to the consumers and to the country itself, that makes us, or that brings a case for to utilize the concept of microgrid for the energy distribution, transmission and distribution of energy in Pakistan as well. So microgrids, again, it's $1 billion industry, and it is driven by the failing costs of the microgrid control technologies, primarily the power electronics that is used in this. So for Pakistan, microgrids can provide a sufficient solution to at least 50 million people which are facing electricity challenges. The reason is that there are lots of areas where our national grid is not reaching, where the local distribution companies are unable to provide electricity. So the benefit for this, or this sort of situation, is that we only need to have a common point of coupling with the grid, and we can independently generate electricity for a small village or a small locality, and we can distribute that electricity throughout that certain locality. And we can also utilize that sort of grid in an islanded mode, that for example, if we are not going to connect it with the normal AC grid of Pakistan and the national transmission network of Pakistan, that is fine. That system is robust enough to generate its own electricity and distribute its electricity to its consumers. So comparing the concept of microgrid and the legacy power system, we see that the microgrids are compact version of the traditional centralized power system. So microgrids are and they are also capable of generating and storing their own energy through distributed generating units. So when in this work, remember, when I'll be using the distributed distributed generation, it means that the generation is done with the help of photovoltaics, or for example solar or wind, in primarily in both cases. So then again, the concept of coming back to this, the microgrids, they can function in two modes. One is the grid connected mode, where the microgrid is connected to the legacy power system or to the main centralized power system with the help of point of common coupling. And it can also help, and it can also work in an islanded mode, or it means that it is an independent unit that is generating its own electricity, storing its own electricity, and distributing its own electricity. Then the power generation takes place much closer to the consumer. So in this, the concept of microgrids, what happens to us is we save a lot on the transmission cost. For example, we are generating huge amount of electricity in Pakistan at Tarbela, and that electricity, we are taking that electricity from Tarbela to Karachi, and that takes a lot of cost, a lot of losses, and lots of infrastructure to do that. So for what if we are going to use, or we are going to use the solar and the wind that is available to us near Karachi, and we are going to power, or we have that sort of system that generates that electricity from wind and solar and distributes it to the community in Karachi. And that is the concept of microgrid, is that if you have your own generation, you can easily distribute it without the help, or without bringing into the high transmission of electricity or the cost that are associated with it. So again, it is that makes it much more efficient than the conventional power system, and it also allows bidirectional flow of electricity. So if for example, if a consumer is also generating electricity, it can also supply to the network. So if there is a big generation of a big wind and a solar generation, and there are certain consumers that have also PV or photovoltaics installed on their homes, they can also those consumers can not only consume the electricity, but they can also supply it to the community. So protection microgrids, how it is different. So remember, when we are going to realize this microgrid, the key aspect is how we are going to have the protection in place. So microgrid protection is a key aspect. And so how, again, this protection is different from the protection schemes what we are using in the centralized microgrid. So the key protection issue with microgrids is that that is in the islanded mode. So once the microgrid is in working independently, that is the reason when we have the key protection issue. The faults are much lower than those in the grid connected mode due to the integration of renewable energy sources. So what happens in an islanded mode, that if a microgrid is operating independently, the fault currents or the fault levels are much lower, because the power generated or the requirement is much lower compared to the big centralized grid. So again, in islanded mode, faults are to be cleared with techniques that do not rely on the detection of high fault current. So again, since the fault currents are not very high, so the microgrid protection techniques do not require very high current fault detection techniques. So thus the plug and play and peer-to-peer functionality of microgrid should not be disrupted by the protection scheme. This is again a very important aspect. So if there are 2 or 3 microgrids that are connected with a centralized scheme, also with a centralized network, what happens if there is a fault on the main line of a microgrid? That fault must not be able to disrupt the operations of the centralized facility, as well as the other microgrids that are connected. Similarly, protection schemes should ensure features such as selectivity, security, and coordination, ensuring that none of the above features are compromised. So these are the things that are primarily required for developing the protection scheme for microgrids. So overall, what we see here, we present some of the current status and challenges that are there. For example, if we see the fault current limiter, so what it features, so the limitations are that it's only applicable for specific types of microgrid topologies, because due to its expense, and it's also the need to select the best location for the series impedance of a microgrid. Similarly, under voltage detection, so under voltage tripping can result in shutting down the whole microgrid in case of a fault in any region. So these are, for example, certain challenges associated with all these the current existing protection techniques. So that is why we have proposed a new mechanism or a comprehensive protection scheme, that if we are going to make a microgrid and we are going to integrate that microgrid with the renewables and also with the centralized facility, what sort of protection scheme would be there to ensure continuous and stable operation. So here here the system design and realization of our network is shown. So we are using the conventional Pakistan uh, grid station supplying 220 volts at 50 hertz. All the transformers are step down transformers, 220, 200 to 11 kilovolts. So on the transmission side, we are considering medium transmission voltage lines, and we have used for our simulation is the ACSR plover conductors or of 100-kilometer length, and these values are taken for NTDC values. Our feeders, so since we are using the values of actual feeders that are used by the K Electric in Karachi. So we are using ACSR Sparrow conductors. So we have found the information for the Gulshan Iqbal. There is a region in Karachi, and then Gulistan Johar. So there is an 8-kilometer ACSR feeder, ACSR Sparrow feeder, and there is a 12-kilometer long Johar feeder in Karachi. So we have used the values provided to us by the K Electric as to make our presentation more realistic. And so figure 1, if we see the figure 1, we have 3 zones. So zone 1, zone 2, and zone 3. We have a static switch, or we can also call it as a point of common coupling, that allows our 3 zones, and those zones to be connected to the main supply or the main NTDC grid network. And this zone 1, zone 2, zone 3 can be considered as microgrids, and they also have their own DG units. So DG means distributed generating units, means that they have either these units they have their own solar PVs or wind generation plants. And for the simulation sake, we are for the simulation we are using solar based generation for this case. So moving ahead, the contributions for the work. So in this work, we have explored and analyzed the existing power system and protection schemes for renewable energy integrated AC microgrids. And we have also developed a comprehensive architecture and an algorithm-based approach, operations and control of protection scheme for the renewable energy integrated AC microgrids. And we have again shown the simulation results, which I'll be talking ahead. So generally discussing types of faults, there are symmetrical and unsymmetrical faults. In the symmetrical faults, we have line to line to line to ground, or LLG fault, and line to line to line fault. Similarly, in unsymmetrical fault, we have line to ground fault, line to line fault, line to line to ground fault. So these are the types of fault which we have considered in our results and in this paper. So again, when we are going to develop a microgrid protection scheme, we have to consider the IEC standard. So IEC standard TC 62893-3-1 that was revised in 2020. It requires the following aspect of protection for any AC microgrid. So the first is the dependability of the protection scheme, that your protection scheme should be dependable enough to allow continuous operation. The security of protection, that there must not be any, it must not allow any cyber attack or these sort of malfunctioning. Then it must allow, or it should have the availability and selectivity of the protection. So in case of one relay or a protection equipment not functioning, must be able to switch to another protection equipment for as a backup. So again, and then clearance time for protection. Clearance time is very important. Generally, the time allowed by the NEPRA to the consumers, to the utilities in Pakistan, is within 2 seconds or within 5 cycles of the waveform, and we are using 50 hertz, so that will help us calculate that. So what we have proposed here is the is a protection scheme that is based on 5 relays, and that are used in such a manner that we have an OR gate in between them, or there is a control logic between them. And these 5 relays are overcurrent relay, differential relay, sequence relay, voltage relay, earth leakage relay. So the protection scheme will ensure the protection against, and in this, and we have developed this, that our protection scheme will ensure protection against all major faults while ensuring selectivity, security, and coordination of a microgrid. So the inputs for our this proposed architecture is the current signal, voltage signal, the neutral current signal, and with the help and sensing these signals, we can generate our trip signals for the coordination and protection of for the operations and coordination of these relays. So overall, talking about the overcurrent relay, the protection module implements the DT or definite time overcurrent, or DTO-CR relay. So we have simulated it in ours for our simulation. We are using this relay for the analysis. And this is used for protecting the system for overcurrent conditions, and the primary purpose is that it protects us from symmetrical faults that are line to line to line to ground fault, or line to line to line faults. It is used to protect microgrid in grid connected mode. So remember, this arrays will not be used in the islanded mode of operation. Similarly, differential relay used for protecting. It is used for protecting electrical equipments like feeders and feeders, transformers, etc. It finds the difference between incoming and outgoing current to detect faults, and if the difference is more than the desired value, it generates a trip signal. Similarly, proposed solution uses this relative protection of feeders from the fault. It also protects the feeder from all faults in both modes. So it means that if you're using this relay, this differential relay is used in both islanded mode of operation and grid connected mode of operation. Then we have the earth leakage relay. Earth leakage relay is used to detect earth leakage faults. The fault occurs in case neutral current is non-zero, and this relay implements directional component to achieve selectivity of protection, and is used to protect microgrid in islanded mode for ground faults. That is an important. So if there is a ground fault coming, so this is the relay that acts, or that is the one we are moving, where we go to in case of such faults. Then we have the voltage relay, and that is used when the voltage is out of range of the preset values, or it's over or under the allowed limit. So under voltage relay for detecting symmetrical faults, addition of time delay to avoid false tripping, and it is used to protect microgrid in the islanded mode of operation. Then we have the sequence mode relay. Again, it computes the magnitude of all sequence components of the given current. If magnitude of a component exceeds the set value, the trip signal is generated. Addition of time delay is used to avoid false slipping, and it is used to detect line-to-line faults for negative sequence and upstream earth fault for zero sequence currents. So this is the usage of the 5 relays which we have used in our proposed protection scheme. So overall, for example, this is a summary of where our in which mode we are using and what is the purpose of the each relay. So this is a summary of that. So for example, the differential relays can be used for all faults, and it's used in the grid connected and islanded mode of operation. Similarly, so there is a NEPRA's standard requirement. So that allows 5 cycles for a circuit breaker to operate. It must operate inside 5 cycles, or failure of circuit break 5 cycle will be backup clearing 9 cycles after the fault. And so if a circuit breaker fails, the stock breaker condition 5 cycle will be and it means that it must be backed up in 9 cycles to avoid this fault, to remove the fault, you can say. So these are some of the requirements which we have used in our case study, and we have simulated this. So this is the simulation, or is the single line diagram of the system which we have simulated in MATLAB, and we have used MATLAB simulating system, Sindh Power Systems for simulation of this. So we have a utility grid, that is our conventional main transmission system, or the NTDC's main transmission system. We have a transformer, we have a static switch or point of common coupling. We have a bus, and then we have a feeder. This is our feeder A, this is feeder B, this is feeder C. Feeder, for example, feeder for zone A, zone B, zone C. So unit A, similarly zone C, zone B. So this is how our single line diagram looks like. So moving ahead, this is a zoomed in version of the Simulink system which we have. So we have, for example, we are naming the zone A as Gulshan and zone B as Johar. And since as we see, as I have told earlier, that we are using the values of the feeders that are provided to us by the K Electric. They have given us the values of feeder for Gulshan Iqbal and Gulistan Johar. These are two regions in Karachi. So we are using these values for our analysis and case studies. So we first of all did some hand calculations. We generated some faults on the buses and we calculated them. So our calculated value and our Meyer values are quite close to each other, and that actually gives us a good idea of how we are simulating that our simulation is working fine and our calculation is also in line with the simulation results, or vice versa. So first of all, let's discuss the feeder fault. So if, for example, we can see that, you can see that the first diagram, so this is the result for the line to ground fault on the load side of zone A. Distributed generation unit of zone B is the bottom current. So for the zone A, we can see that at some point at 0.75 seconds, at 0.75 seconds, the fault occurs. So we can see that there is some current fluctuations, and that fault is nullified within 0.1 second, or less than you can say or less than 0.2 seconds, and the grid or the operation goes back into the normal mode of operation. That is one of the way we can see that our protection scheme is working and our relays are working fine. Similarly, if we introduce a line to line ground fault and in a grid connected mode, so this is also showing the operation of our DTO CR relay. We can see that at again around 0.16 seconds, the fault is introduced again. Here we can see that the load current starts to shift, and the current overshoots. And as soon as the relay operates and trips and removes the fault line, the grid comes back to its normal state of operation. And this again happens within or in less than 0.1 second. Similarly, we also see the situation in case of earth leakage fault. So in earth leakage fault, and this is again the load side of B distributed unit, and below is the current in the graph. If there is a fault, again, what happens that in case of earth leakage fault, the distributed unit is disconnected from the supply, and this is what we have seen that unless and until that ground fault is removed physically, the system should be disconnected from the supply, and that is what our protection scheme has done. So the protection scheme has disconnected the distribution unit from the supply, and we can see that there is no further transmission of power. Similarly, again, earth leakage fault, in this case, the distribution unit keeps on supplying, so the supply keeps on there, and we have seen that again the response time is less than 0.1 seconds, and what we see here is that the earth leakage fault is removed and the distribution of the supply is resumed. Then here what we see is under and over voltage faults. So in this case, again, we see a fault coming at 0.16 seconds. So the fault is there, and once the fault is removed, the voltage levels come back to normal, and that is again achieved within 0.1 seconds. And that is again, you can say within the limits, and that is within the prescribed standard limits for the fault correction. Similarly, the line to ground fault or a sequence relay, again, once this fault comes on a distribution grid current, so the effects or what happens is that once the sequence are aligned, we need to disconnect the distribution grid, distribution generation from the network. So this is what we have seen. As soon as the fault arrived, within or less than or within 0.1 seconds, the distribution generation network is or the system is disconnected from the supply, and the supply is or the grid is saved or protected. So overall, what we have demonstrated here is that we have demonstrated modeling of a renewable energy integrated AC microgrid using actual parameters obtained from the Karachi Electric Company. We have demonstrated via simulation the protection architecture and the algorithm based for all sort of fault conditions. And we have also given an analysis of ample fault conditions in islanded and grid connected modes of operation. So again, these are the references which we have used in our work. And so thank you for listening, and I'm open for questions if you have. So again, thank you very much.